All right, so we're going to start off today by looking at section 3.2, which is really on three different things: okay, continuity, intermediate value, and what's called end behavior. Okay, so some of these, they all have to do with graph. Okay, kind of visualizing something on a graph. That'll help us with all three of them. And we're going to start off by looking at what's called continuity. So most older graphing calculators assume that everything you draw on the screen, you want it to be connected. So even some of the newer calculators, depending on how you have it set up. So let me show you a graph of the step function. Remember, we've looked at the step function before. It looked like horizontal lines. And this is what the step function should properly look like. Let's see, int x tick graph, and that's exactly what the step function should look like. Notice it's not connected. Okay, there's these jumps in the graph, right? It's not what we call continuous. Right? You'd have to pick your pencil up as you were drawing it. This is what an older calculator would draw the step function like. Notice it does it faster, and it's trying to connect every step. Okay, well, that shouldn't happen. Okay, so there's a newer feature on these calculators and probably other models as well called detect asymptotes. So if you ever notice you have a graph, here's another example. Let's do 2 divided by x minus 4, but let me put the 2 in parentheses, the denominator in parentheses. Now you can't plug 4 in for x, because if you plug in 4, you're going to divide by 0. So watch what happens when x gets close to 4. It tried to connect two parts of a graph that shouldn't be connected. This is not what it should look like. What it should look like is this. And you notice it draws it a little bit slower, because it has to think a little bit more. But that's exactly what it should look like. Right? So if you ever get a graph that sometimes has this really steep vertical spike in it, and it's connecting two parts of a graph that maybe looks like it shouldn't be, probably it's because it shouldn't be connected. And on these calculators is a way we can adjust for that. So I'm not going to graph this one. I just graphed something almost exactly like that. But you can see what happens when you divide by 0. You can get this weird connection that your graph calculator wants to do that shouldn't be there. Right? Now, we graphed this one and we graphed this one. Can you trace either one of these graphs, and I still have one of them up on the screen, without lifting your pencil? No, this is two distinct parts to the graph. There's no way to trace this part and then get over to the next part without lifting up, putting it down somewhere else, and starting to draw again. Okay. Now, if we look at something like this is a parabola. Okay, it's been shifted a little bit and transformed, but can you draw a parabola without ever picking up your pencil? Yeah, that's fine. That's just a U shape. Whether it's a U shape that's opening up or opening down, you can always draw a parabola from beginning to end without lifting your pencil. So these first two are very different than this bottom one. Okay? And we're going to talk about what the word is to describe that. And it has to do with what's called a continuous or function or continuity. And sometimes we can find maybe a small section that's continuous. If we can't draw the whole thing without lifting our pencil, maybe we can draw a small part of it without lifting our pencil over a certain interval. So we say that a function is continuous over a specific interval, meaning from a start to an end, if basically when you're drawing from the starting point to the ending point, you would never have to lift your pencil between those 2 points. If that is true, then we can say between points A and B, we have a continuous function, at least between points A and B. If you can't do that, then the graph is what we call discontinuous over that interval. So let's say I had a graph that went like this. Just have a shape here, and then it does something else over here. And they don't connect. Let's mark a few points. A, B, and C. Could I draw from the interval A to B without lifting my pencil? Yes. Then we could say that the graph is continuous over the interval from A to B. Now, could I draw from B to C without lifting my pencil? No, can't do that. So we would say that this particular graph is discontinuous over the interval from B to C. How about A to C? Could I draw from A to C? No, can't do that either. All right. So this particular graph has some areas that are continuous, and I can find other intervals that are discontinuous. And that's what I just said. So let's look at a graph, and instead of just using like letters A, B, and C, let's use a specific graph and an actual values, and let's find two intervals that are continuous, meaning you give me a start and an end, and I could draw between them without lifting my pencil. And then I want you to give me two intervals where it's discontinuous, meaning if I tried to draw from where you're telling me to start and stop, I would have to lift my pencil. So it's going to look very similar to the graph I just did. 1 over x. So you can see it's in two distinct pieces. And those pieces should continue up and down forever. They're what we call asymptotes to the y-axis. It looks like they stop, but that's because when things start to get very steep on the calculator, it can't draw it anymore because it's going almost straight up and down. Okay, so remember, when you name an interval, you give me x values. So let's start with continuous. Could somebody give me an x value that I could start at and an x value that I could stop at, and I could draw between those two along the graph without lifting my pencil? Yep, John?
2 and 4.
All right, so 2 would be right there on the graph. 4, I'm just marking it, would be right there on the graph, and I can definitely draw between 2 and 4. Now, when it says interval, you could do an open interval, you could do a closed interval, you could do a half open. That doesn't really matter. All right, so I'll just do it as a closed interval. You could trace from 2 to 4, including 2 and including 4. Can somebody give me another interval that you could trace from the start to the end without lifting your pencil? Mike?
-5, -1.
All right, so if we go -1, we're about right there. -5, we're about right there. And I can definitely trace between those two without lifting my pencil. All right, so those are two intervals where it's continuous. Now let's do discontinuous. Basically, what number do you have to go through here so that you have a discontinuity? As long as you start before this number and you end after this number, you're always going to have to lift your pencil to do that. John?
0.
0. Anything that starts before 0 and ends after 0, you're going to have to lift your pencil. So, -1, 2, 3, and I did an open interval. Again, I could do it open, I could do it closed. It doesn't matter how you want to do it. But you can't trace from -1 to 3 and have it be continuous. All right. You can't trace from -8 to 34. Can't do it. So as you can see, there's an infinite number of answers to this type of question. Any questions on that? So let's look at the integer function again. That's a step function. So let me put that one back up. And the question is going to be, what is the longest interval in this function that is continuous? What's the length of the longest possible interval you could find there that is continuous? And remember, technically, when we draw the step function, let me make it bigger. It should look like this. We have a closed circle on this end and an open circle on that end of each step. Nick?
-2 and -1.
So what would be, what's the actual length?
1.
1. Basically, just under 1. What would be exactly 1? Yeah, you could basically say that it's 1 unit. That's fine. So you could trace along this step, and that step starts at 0, and it ends at 0.9 repeating. Right? The next step starts at 1, and it ends at 1.9 repeating. Okay? So that's the length of the longest interval that you can possibly have in the step function that is continuous. Any question on that? Okay. So there's different reasons why you might have to lift your pencil when you're drawing a graph. The reason why you have to lift your pencil in this graph has to do with dividing by 0. Because you can't divide by 0. The reason why you have to lift your pencil in the step function has nothing to do with dividing by 0 at all. It's a totally different reason. So we're going to look at some of the reasons, or some of the things that can cause your graph to have a discontinuity. First of all, you can have an undefined value. Okay, an undefined value. And as we saw in a graph like this, when you get close to an undefined value, your graph goes up to infinity, or it goes down to negative infinity, just like this. It goes up, this should just keep continuing up, and that would continue down. So that's one thing that can cause your graph to have a discontinuity. The other way you can have a discontinuity is if you have a break. And this occurs in the integer function just because of the way we round. Okay? This means to round to the... So the greatest integer function means tell me the biggest integer you can think of that's less than or equal to what you plug in right there. Well, just by the definition, if you're always telling me an integer, then you're never going to get a y value of 1.3 out of this formula. You can get a y value of 1, you can get a y value of 2. There's nothing in between. You jump. So because of the way we round, it causes us to jump, and that creates a break in the graph. Not because we divided by 0, though. And the other one we can have is kind of tricky. It has to do with having an undefined value, but it's not as obvious. When you have a graph like this, extremely obvious that it's an undefined value there, because you have two parts of the graph curving in opposite directions. Well, let's graph this. What do we know that you can't plug in for x in this last example? Yeah, Tim?
-2.
Yeah, you can't plug in -2 because it would cause you to divide by 0. And we might think, yeah, well, I know what it looks like when you divide by 0. You get those parts of the graph that curve in opposite directions. Well, let's try this one and see what happens. So I'm going to type in x squared plus 3x plus 2. And I'm going to divide by x plus 2. I'm going to hit graph. Does it look like anything weird is happening in that graph? I can make it bigger, I'm not sure it's going to help a lot, but does it look like anything is happening at -2? It does? What do you think is happening at -2?
Well, it's just crossing the x-axis.
So at -2, we're
Oh.
right there. That's at -2. Anybody see anything strange about that spot at all compared to anything else on the graph? Yeah?
Looks maybe slightly thinner. I
It
can't
looks
tell.
slightly-
It looks like there's something like weird with the line going on.
I think that's just the plastic.
Yeah.
The plastic makes it kind of like hard to make it wobbly.
So I don't think there's anything there happening that's not happening somewhere else.
Yeah.
I mean, it does kind of have like a little jagged spot every now and then, actually pretty uniformly, but I don't see anything there that's different than anything else anywhere on that line. So the tricky thing about this is if you look at a graph, you can't find this discontinuity. I can go to the table and I can plug in -2 and it'll tell me it's an error. It'll tell me that you can't plug in -2 because you're dividing by 0. If I plug in -1.99999, that's perfectly fine. It doesn't give me an error. If I plug in -2.000001, that's perfectly fine. It doesn't give me an error. Again, those numbers are not really -2, it's just rounding it. But when you try to plug in exactly -2, you can't do it. And the only reason you would be able to figure that out is by looking at the original problem. How does the numerator factor? X squared plus 3x plus 2. Yep.
X plus 2 and x plus 1.
X plus 2, x plus 1. What do you notice about the factors in the numerator and the denominator? Yep.
You cancel out leaving just x plus 1 to divide by 0.
Right. Basically, this graph is this graph. It's almost the same thing. And it looks the same. It's not exactly the same. This graph, if we were going to draw it properly, should look like this. If I could erase that section right there, it should look like there's a hole in the graph right there. So we go on, hole, and then it would continue on. And the hole is not something that you can see by graphing it. You can only figure it out by looking at the original problem. And most of the time you have a hole when you factor the graph, or factor the equation, and you end up with the same factor in the numerator and the denominator. So I could mess this up by just changing that +2 to a +3. Okay, let's just change that one thing. Now, the numerator doesn't factor as x plus 2, x plus 1 anymore. Okay? So it's going to look very different because it's not going to be something that we cancel out when you factor it. So it starts off kind of looking the same, but look what happens when you get near -2. It does that behavior that we're used to seeing, right? One end goes up, the other end goes down. Okay, any questions on that? So just by changing that one number, +2 to +3, I've completely messed it up so there's not a hole in the graph anymore. Now it's more like this case. It's just an undefined value. So you can think of a hole as an undefined value, but it's special because you can't see it on the graph. Even if you keep zooming in, you won't see it. You can only get it by factoring. So every polynomial that we work with is continuous everywhere. Okay, remember, polynomials are things like parabolas, or if you had a cubic function, it might look like that. But the point is, you can't find an interval on a polynomial where you'd have to lift your pencil to draw it. It's impossible. Think of like the simplest polynomial is a line. Do you have to lift your pencil when you're drawing a line? No. So with your pencil when you're drawing a parabola? No, never. Never happens. So technically, just to be clear on this last one, that's not a line in blue. Looks like a line, it's not a line. It's really two rays. Well, it has a hole in the middle of it, so it's not a line. It's kind of like a ray, I guess, two rays going in opposite directions. Okay, so every polynomial is continuous everywhere. And if you have a function that is continuous no matter where you start and where you stop, then we call that a continuous function. The step function is not a continuous function. Yes, can you find small sections that are continuous? Sure. Is it continuous everywhere? No. Okay. And I'll come right back to this, but I just want to go back to the first thing that I drew. Is this graph right here a continuous function? No. Are there parts of it that are continuous? Yes. But it's not a continuous function. A continuous function means you can start anywhere you want, you can stop anywhere you want, and you'll always be able to trace between those 2 points without lifting your pencil. Okay, any question on that idea? Right, so that's continuity or talking about continuous functions. So the next thing is what we call the intermediate value property. And the way I like to explain this is, think of an example like you're boiling water. Okay, and the water starts at room temperature. Maybe it's like 70 degrees. And you're going to heat it all the way up to boiling. So it starts at 70, and you're going to heat it up to 212 is boiling. What temperatures is the water going to go through as it warms up from 70 all the way to 212? Or even how many temperatures is it going to go through? John?
Theoretically, with calculus, it would go through every real number.
Yeah, it's going to go through every single real number between 70 degrees and 212. There will be an instant in time where the temperature is 80.7215436 degrees. Might be a very short amount of time, but it will go through every single intermediate value between the starting point and the stopping point. Right? Think of somebody's age. Right? If you're, 10 years old, and as you go to 20 years old, what ages do you go through in between? All of them. There will be a time when you're exactly 10.5 years old. There will be a time when you're 14.6127 years old. Okay? You go through every single one of them. And that's because both of these are examples of what we call a continuous process. There's no jumping when you're heating up water. Okay? There's no jumping when you're getting older. An example of something that's not continuous would be like counting. Right? If we were counting the number of desks in this room, right? Say we started at 1 desk and we counted all the way up to 28 desks. Do we go through every number in between? Real number? No. We go 1, 2, 3, 4. We never do 4.5. We never do 5.7. That's not a continuous process. Right? So the idea of intermediate value basically has to do with the idea that you're continuous from your start to your finish, and it means you're going to go through every value in between. Okay? That's kind of the simple way to say it. So let me write that out a little bit more mathematically. So it starts off by saying if you have a function that is continuous on the interval from a to b, then your function will be able to take on any y value between the y value you get when you plug a into the function and the y value that you get when you plug b into the function. draw that out as a picture. Let's say we had something like this. This is A, this is B. So what I'm guaranteeing you by saying all of this is, let's say that this y value was up at 2, and this y value was up at 5. I guarantee you, you're going to go through every y value between 2 and 5 at some point. You might even do a little bit more. Like in this case, if I put in a line, that represents 2, that represents 5. You do go through every y value between 2 and 5. Some even more than once. You even go lower than 2. Well, I can't guarantee that. Can't guarantee that you're going to go lower than 2. But I will guarantee you go through all these values in here. The y value at A and the y value at B. Any question on that? Okay, another way of kind of thinking about the same thing is pick any number you want that's between, like in my example, 2 and 5. Any value that you want. If you pick a value between 2 and 5, like 4, there will be a number that you could plug into this formula. If we knew the formula that made this graph, I'm going to call that number C. And when you plug in the number C into the formula, you'll be able to get 4. This number right here could be anything between 2 and 5. And I guarantee you there's a way to calculate that number by plugging in a certain value into the function. And that value that you plug in will be somewhere between A and B. Now, if you pick a number outside that interval, let's say you pick 7, there's no guarantee that you're going to be able to plug in a number between A and B and ever get a result of 7. And in this case, it's impossible. This graph never hits 7. Only guaranteeing you that you're going to hit a y value between the starting y value and the ending y value. And that's called the intermediate value theorem. So let's look at this one. So we have a function, f of x equals 3x minus 4. And they're saying determine the number you would have to plug in for x to get 15. So basically, we're just going to be solving this equation for when we hit 15. What x value would I plug in to get 15 for y? But the first thing I like to do is see, is that even possible? Let's see what we're starting at for a y value, and then let's see what we're ending at. And see if 15 is even in the middle. Because if it's not in this red area, then we're not going to be able to do it. Okay, so let's start by plugging in negative 10. All right, so let's find f of negative 10. So that's 3 times negative 10 minus 4. And Caleb, what does that give me?
You want the whole thing out? Or
Yeah, final answer.
that'd be negative 34.
So on this particular graph, over this interval, we're starting at a y value of negative 34. Now let's see how high we end up going. So now we're going to plug in 10. 3 times 10 minus 4. And Madison, what does that give me?
26.
26. So remember, this is a line. It's a polynomial, but even more specifically, it's a line with a slope of 3 and a y-intercept of negative 4. You're going to start at negative 34, You're never going to lift your pencil, and you're going to end up going all the way to 26. Will you go through 15 at some point? Yes, you will. So now the question is where? That's what they want to know. Where will you go through 15? So all we have to do is fill in 15 and solve for x. Now if they said to me, find where I hit 57. Well, I never would hit 57 on that interval. So I could solve for where you hit 57, but it's going to be bigger than 10. Okay? So I would never hit it on that interval. Okay? Only numbers between negative 34 and positive 26. That's like this red zone of numbers that I'm going to hit between A and B. All right, so fill in 15 equals 3x minus 4. So we're going to get 19 equals 3x. And we get 19 thirds, which is just over 6. Okay, 6 1/3. And that is definitely in the interval, and we already knew that it would be. 6 1/3 is between negative 10 and 10. So any question on that idea? And again, what numbers are you going to hit between negative 34 and positive 26? Yep.
All real numbers.
All real numbers. So there is a spot where you hit 10.4172645? Yep. Somewhere. There is. Because this graph is continuous. Okay. So the last thing we're going to take a look at is what is called end behavior. So this has to do with visualizing what a function looks like. Okay, it's kind of like the big picture. We don't care when we're looking at end behavior about all the little twists and turns in the middle of a function. When we're looking at end behavior, you're focusing on what the ends look like this and like that. This is an example of an end behavior that is up on the right, up on the left. There's 4 different variations you can have. Up, up, down, down. One end is up, one end is down, and then switch it. One end, the other end is up, and the other end is down. And as far as these details in the middle, end behavior doesn't care about any of that. It just cares about what do the ends do. And you have 2 options for each end, up and down. So it's the behavior at the extreme left and right ends of your graph. Even if I were to erase all this in the middle and put a big question mark there and I don't know what's happening, I don't care what's happening. I can still tell you the end behavior is up on the left, up on the right. Okay? And we'll talk about different ways that we can describe that. And just by looking at something like this, I can tell you that that's up on the left, up on the right. I shouldn't have to graph that at all. And I know that's what it's going to look like. If I did this, now I can tell you it's down on the left, down on the right. And if I did something like this, I could tell you that that's up on the left, down on the right. Right? So it all has to do basically with the highest exponent and the number in front. Okay? So let's look at x cubed. Okay, y equals x cubed. Right, so the simplest cubic that you can have. And the behavior here is down on the left, up on the right. And it never really takes a turn in the middle. We know that cubics can, but this one doesn't. So one way we can describe the behavior is kind of using this notation, using these arrows. the left side of the parenthesis is telling me what's happening on the left side of the function. The right side, or the second number in the parenthesis, is telling me what's happening on the right. So if you look at the graph, down on the left, it's going up on the right. Now the other way we can describe the same thing is to use what we call limit notation. And we're going to see a lot more of limit notation if you take calculus next year. So let me just describe or read what this literally means, and then I'll kind of break it down a little simpler. This says the limit of f of x as x approaches infinity. That's how you pronounce that properly. The limit of f of x as x approaches infinity. The limit of f of x as x approaches negative infinity. And what that means, if you kind of simplify it a little bit, is it basically says what's happening to the y value as x gets really big. That's what it means. What's happening to the y value as x gets bigger and bigger. So as x gets bigger and bigger, that means you're heading to the right. So what's happening to the y value in this graph the further to the right that I head? Yeah? And it's what is it increasing toward? Infinity. So as I get bigger and bigger and bigger number, the y value is approaching infinity. Now the bottom one says, what's happening to the y value as I head to the left, as I approach negative infinity? So what's happening in the graph the further and further left that I go? What's my y value getting? What's my y value approaching? Yep, Madison? Negative infinity. So it's the same, it's still describing the same basic idea as what's in the parentheses. This is a lot more formal. You won't see anything like that on the left in calculus. You'll see it like this.
Well, could it not, like, could it do something other than approach infinity, negative infinity? Could it approach a certain number?
Yes, but not with a polynomial. Yeah. So if you had a graph, like let's say you had something like 2 divided by x, let's put this in parentheses. And now by putting a variable in the bottom of a fraction, that's not a polynomial, so this is chapter 4 now. And if you look at what happens as you head to the left and the right on that graph, it's leveling off. It is approaching a value. And you can tell what it's approaching by going to the table and plug in a big number for x. Well, if you try 10, you're at 3.2. If you try 50, you're at 3.04. If you put in 200, you're at 3.01. So it's getting closer and closer and closer to 3. And eventually we would know that just by looking at the formula that I typed in to graph it. So yes, it can approach values besides negative infinity and infinity as you go further left and right, but not in a polynomial. So in a polynomial, there are only 4 types of end behavior. Up on the left, up on the right, down on the left, down on the right, and then one of each. And as I said, eventually we're going to have a chart that you should be able to figure out what the end behavior is without even graphing it. In fact, I might give you a problem you can't graph, and you'd have to find the end behavior. All right, so let's look at this one. So f of x equals x to the 4th and negative x to the 4th. So what we're playing with here is seeing what happens when the number in front of the highest degree term is a positive compared to when it's a negative. And we're also looking when the exponent is an even number. So let's do x to the fourth and negative x to the fourth, just like it's written. So x to the fourth is going to look kind of like a parabola, but it's going to be a little flatter on the bottom. Might be hard to see. It is a little bit flatter. And negative x to the fourth causes a reflection. Okay, remember, when you put a negative in front, it flips it over the x-axis. So how would you describe the end behavior of x to the fourth? That's the one in blue. What's happening on the left? What's happening on the right? Get it?
Left up, right up.
Yeah. So it's up, up, if you wanted to describe it that way. And if you want to do it as limit notation, it's exactly the same. Oh no, it's not the same as x cubed. So I'll do this one in limit notation just to show you. So the limit of f of x as x approaches infinity, and the limit of f of x as x approaches negative infinity. These are always the two questions you have to answer to describe any behavior. So Sophie, what's happening as we head further and further to the right in x to the fourth?
It's increasing.
And what does it approach?
Okay.
Approaches infinity. And Maddie, what happens as we head further and further to the left?
It approaches infinity.
That also approaches infinity. Yep. So in a polynomial, when you're using limit notation, this answer is either infinity or negative infinity. Now let's describe x to the fourth. I'm not going to do this one as a limit. We'll just do it using the arrows. So Lindsay, what's the end behavior of negative x to the fourth?
Down on the left, down on the right.
Yep, down on the left, down on the right. So remember, this side is always describing the left. That side always describes the right. Okay, any questions on that? Yep.
So basically, if the exponent is even, it's the same, and if it's odd, it's down and up, and then the negative depends on whether it's down up first or up down first, or if it's both up, both down.
So yes, the exponent controls whether the end behavior is in the same direction. If it's even, it always will be. And then the negative controls whether things are up or down. So in the case of an even, a negative means both down. In the case of an even with a positive in front, it means both up. And again, I'm going to make a little chart that kind of shows all that. So notice, all you have to look at is the highest degree term. That's how I was able to tell you the end behavior of that complicated polynomial without graphing it. This stuff may cause little twists and turns, but it doesn't matter at all. You could change anything you want that I underlined, wouldn't affect the end behavior. Okay. So this particular one is an odd exponent, positive number in front of x. So if I look at my chart, odd exponent, where the leading coefficient is greater than 0, means that I'm going to have a down-up behavior. So again, as Tim pointed out, even, it's always in the same direction. Odd, you have one of each. And then whether the leading coefficient is positive or negative, kind of gives you the final piece to the end behavior. And remember, this all applies to polynomials, which is a very specific kind of function. If you want to start talking about some of the other things, like someone said, can you approach a value that's not infinity? Now you're talking about things that aren't polynomials. That's different. Okay, so any questions on that chart? So that shows us our our four different cases that we can have. I don't think there's anything else there. So the leading term in a polynomial, remember we call that the term with the highest degree. It would be nice if the leading term is always in front, but sometimes it isn't. So if you had something like this, you'd want to be careful when you describe the end behavior because the term you're focusing on is negative 8x cubed. So usually the leading term is the term with the highest degree if we put it in descending order. That's not in descending order. So that leading term with the highest, or the highest degree term, that term basically controls what the polynomial is going to look like. None of the other terms make a difference in terms of the end behavior. Now, if you're solving for roots or finding where it crosses another graph, then yeah, everything's important. But if all you care about is the end behavior, it's just the term with the highest exponent that you need to worry about. That term alone predicts the end behavior. So we're going to talk about what's called an end behavior model. A very simple idea. I'm going to call it EBM from now on. So the EBM, if you look at some long polynomial, the EBM is just the highest degree term. And what that means is if you were to graph f of x and you were to graph g of x and you were to zoom out enough, they would basically look identical. Yes, f of x might have some little twists and turns and other things because of these other terms, but if you zoom out to infinity, as far out as you could, and look at the big picture, these two graphs would pretty much look exactly the same. So f of x is just a long polynomial, and then g of x is the highest degree term in that polynomial. And g of x is called the EBM, end behavior model. So, I think that's it. All right, so what they want us to do here is graph f of x and g of x using different windows. One window is going to show us all the little details about the graph. The other window is zoomed way out. In fact, it's zoomed so far out that the EBM is basically going to look exactly the same as the original function. Even though the original function has all this other stuff in it, it's not going to matter when you zoom far enough out. All right, so let's type in 2x cubed minus 7x squared minus 8x plus 16. And then we're just going to type in 2x cubed. And they tell us the window to use. So we don't have to guess about what kind of window we're going to use. We're going to use what they tell us. Negative 8 to 8 on the x. And negative 100 to 100 on the y. 100 to 100. Now let's hit graph. So here's the original. And here's the end behavior model. Okay, do those two graphs look the same? Do they look like they're right on top of each other? No. It's because we're not zoomed out. We're zoomed way in. So we're kind of focusing on all the little details. I'm not going to change anything about my graphs. Let's just zoom out and get a bigger picture feel of these two graphs. So let's go negative 40 to 40 and negative 10,000 to 10,000 and hit graph. Okay, so now again, what you're going to be seeing first is f of x, which is zoomed out. And now we're going to look at g of x. How close do those two functions look? They're pretty close, right? So if you're trying to predict what this function basically looks like, it's not exact, but it's pretty close. What it basically is going to look like is 2x cubed. None of these other terms made a difference at all in the big picture. In the zoomed in picture, yeah, absolutely. Okay, but not in the big picture. So that's all I want to show you for number 7. Okay, what an EBM looks like compared to the original graph. Okay, and number 8, find the end behavior model of that. And the end behavior itself. So what's the EBM for example 8? Well, maybe. Yeah. So that's the end behavior. What's the actual model? Yep.
Negative 0.5 x to the fourth.
Negative 0.5 x to the fourth. That's the EBM. Now, describe that and tell me what's going to happen. And what did you say? Yep, that is going to be down and down. Down, down. Any question on how we figure out what's down, down, or why that's the EBM? All right, let's look at our last question. So it says, we do a lot of these kind of rectangle variation problems. Find the maximum area of a rectangle that has its base on the x-axis and its upper two vertices on the graph y equals 4 minus x squared. I'm just going to have to think about that a little bit. I think the easiest way to do this is going to be to make a sketch, because that's kind of hard to visualize. So find the maximum area of a rectangle that has its base on the x-axis and the upper two vertices on the graph y equals 4 minus x squared. So this is going to be an upside down parabola, because we know it's down, down. Right? It's going to look something like this. So if this is my x-axis, the maximum width of the parabola is going to, or the width of the parabola is going to control the width of the rectangle. Because if my 2 points were like here and here, then there's my rectangle like that. Right, so that's basically what we're looking for. All right, but we want the maximum area that we can get. So you could also have 2 points like this. Okay, that's also a rectangle. So we're going to try to find the biggest one that we can. All right, so let's graph, and I'm going to use my table to kind of help me out with this. 4 minus x squared. Go to my table, and we'll just get a few values. Okay. Oh, I already had it drawn. So, just to show you, I got the point 0, 4. That was 1 point on my parabola. Then I did the point, looks like 1, 3. So 1, 2, 3. And it's going to be symmetrical. So negative 1, 3 is also a point. Right, so any question on that? So the base of your rectangle is going to always be along the x-axis. And these 2 points, these corners of the rectangle, always have to stay on the parabola. You could put them up here if you want. Make your rectangle like that. That's fine. But I want to find the one with the biggest area. Yeah?
How did you find that was the biggest area?
That's just a sample of one of the rectangles. I don't know if that is the biggest one. That's just a sample of I picked two random points somewhere on the parabola, and I drew the rectangle like that. So that may not be the biggest one. Right, so any thoughts how we can figure that out? Trying to find the rectangle with the biggest area. Let's think about that. Yeah. Go ahead.
So, are the rectangles with biggest areas squares?
So we do know from past problems that the rectangle, in quotes, with the biggest area does happen to be a square. Yes. So is there any way that we could use that information to help us? Yep.
Well, we'll just need to figure out how to make x equal y, right?
Yeah, so we just have to figure out how to make that a square, and some people may not even remember that that's a square. So technically, you don't even have to remember that. Let's think about what the height of my rectangle is going to be, and the width. Because if we can find the height and the width of my rectangle, then all we have to do is multiply them together, and we'll have a formula for area, and then we can put that on the calculator, graph it, and calculate a maximum. All right, so even if you don't remember that it's a square, that's okay. So think about the height. How would you find that height? Like, how would you find how high up you have to go from here to there? Yep.
Well, would you use the calculator and use like the list of the max value?
And what would you be plugging the x value into?
The formula.
Yeah, this formula tells you how high your y value is based on plugging in an x value. This tells you the height of the rectangle. So let's say you plug in 0. What would the height of your rectangle be? Well, if you plug in 0, you would be up there. What's the height if you plug in 0? 4 minus 0 squared gives me 4. So that would be a height of 4, which in this case is just a line segment. It wouldn't even be a rectangle. So the height is given by 4 minus x squared. How about the width? Yeah?
Wouldn't that be given by 2x?
Yeah, it would be given by 2x, because the number that you plug in from here to here, that number is x. Well, remember that a parabola is symmetrical, so this distance is also x. So the width of the rectangle is 2x. So this represents y, this represents x. So yes, if you remembered that the area, the maximum one is a square, all you'd have to do is set that equal to that, and that should give you the answer. But if you didn't remember that it's a square, area of a rectangle is the height times the width, or length times width. 2x times 4 minus x squared. And only certain values of x would make sense in this problem. Anybody tell me what I couldn't really go bigger than because it wouldn't make sense? It might be easier if I erase this so you can see it a little better. Or actually, even if you just look at this, it should tell you what x can't be bigger than, because then it wouldn't work. Yeah?
It'd be 2.
X can't go bigger than 2, because then you would have negative height, and it says specifically that the rectangle is on top of the x-axis. Okay? It doesn't go under it. So x can't be bigger than 2. And it also can't be less than 0, okay? Because then if x was less than 0, that wouldn't make sense, because think about, well, you tell me, why can't x be, why does x have to be greater than 0? Yep.
Because you can have a negative way.
Yeah, if x was like -5, right, you would do some calculation inside here, and then if you multiply 2 times -5, you get -10 times a positive number there. That would give you negative width, so we don't want that. So let's graph that and just look at between 0 and 2. All right, so I've got my height was 4 minus x squared. My width is 2x. And we're only going to look between 0 and 2. And let's set this negative 10 to 10. So it's just like our standard window. And sure enough, we do get a maximum in that area. Okay, so let's calculate it. And we already know that when we calculate it, it should come out to be a square, and we can check it. So let's go left. Let's go to the right. I think we're good. Do our guess. And it says the maximum is when x is 1.15. So x is about 1.15. Let's plug that in and see what it gives us for a height and for a width. Bless you.
Thank you.
So I have, all right, you know what I'm going to do? I'm going to plug them in on a y1 and a y2 so I can see both values at the same time. I've got the answer. Let's put that as 2x. Go to the table. And I'm going to type in 1.15 and hope that I get roughly the same number in y1 and y2. Let's see. So in this case, did we get the same number? No. So then what that might mean is because we did this with the restriction of this parabola, that idea that it's going to be a square might not apply. Usually that usually is the biggest area, is a square, but we have this restriction of a parabola, so there could be something there that messes that up, because 1.15 is the correct answer. So we did it correctly. I'd have to think more about why the square idea doesn't work. But here it's not working. Yeah?
When you look at both functions together, the parabola goes below, like the maximum goes above the parabola, the actual function, I can't, 4 minus x squared, like that parabola, our area equation goes above it so that the maximum is greater than the parabola.
Okay. So in this case, yeah, it doesn't end up being a square, but I think as long as you understand this, that's the important thing. The height of your rectangle is 4 minus x squared, and the width is 2x. And then the calculator can give us the maximum from there. Right, so find the maximum area. I would have to plug in 1.15 and see what that comes out to. So it's 2.6775 times 2.3, whatever that comes out to. 2.67 times 2.3, and that gives me a max area of about 6.1. Okay, that would be, the book said 6.16. We got 6.14. So, yeah, pretty close. Max area, about 6.14 square units. Any question on that? but not too bad if you try to draw it out. Alright, so that's the homework for tonight on page 161. Okay, it's 1 through 6, 9 through 12, 15, 16, 21 to 25, and 29 to 31 and 33. Okay, we'll take a look at that tomorrow, and then tomorrow will be section 3.3, and Thursday will be section 3.4.